Hi, welcome to the problem session for Lecture 5, covering integrals in one dimension. Okay, so we're going to do a bunch of examples here, starting with a relatively simple one, just to get started. 4x cubed. So now we're going to use some rules here. So we're going to use the rules that this equals that. And so the integral is also linear operator, and this equals that. So the power rule, you add 1 to the exponent instead of subtracting 1 as you do for derivatives, and then you divide by the new exponent instead of pulling down the old one for integrals. And don't forget the constant c at the end here. This is for n does not equal -1. We can use that rule here. So the integral of 4x cubed equals 4 times, there's a dx there, sorry, 4x cubed dx equals 4, you're going to pull down the 4, so it's 1/4 x to the 4th plus c, or just x to the 4th plus c. There you go, there's our example. I'll do another one on the same screen. Similar one to x to the 4th plus 6x minus 3. Again, we're going to use same rule, except now we're going to use a slightly more complicated version of this one, which lets us split up the integral using its full linear operator glory into these two integrals. Basically the same idea as the previous one. And we're going to use the exact same rules again to get the integral of this f of x dx is going to be 2 times the integral of x to the 4th dx plus 6 times the integral of x dx minus 3 times the integral of dx. That's going to equal 2 times 1/5 x to the 5th plus 6 times 1/2 x squared. Note the 1/2 and 1/5, those mirror the new exponents according to the power rule, minus 3x, same here, because here you're integrating x to 0. And don't forget the c at the end of the whole thing. Technically all of them have c's, you can shove the c's together, it doesn't matter, it's a constant. And we're done. So it's 2/5 plus, I guess we can simplify to get 2/5 x to the 5th plus 3x squared minus 3x plus c. Okay, there we go, that's done. Okay, so there are a couple of examples that are, I think, relatively straightforward. Now we're going to move on to the next one. This one's from the book. This one's a bit tricky, so I think it's useful to go through here as well as the book. We're going to integrate this function. Don't worry about the fact that I'm reading it like this. That's from the book. This is our function of f we're going to integrate. Now this is tricky because our first glance looks like a substitution kind of problem because we have a composition, right? It's the log of x squared. So it looks like we have a composition, and we naturally try to think of substitution when you have compositions, which is what we do always when we do, if we're doing derivatives. We would have f equals h of g of x, and we would set h equal to the log and g equal to x squared, and take the derivatives using the chain rule. So the natural impulse of us here is to use the complement of the chain rule for integrals, which is integration by substitution. We talked about it in the lectures. However, this is not going to work for that, because if you notice, for substitution to work, right, what must be true? Well, we must have some multiple of the derivative of the inner function, the composed function, multiplying the outer function, right? So it needs some kind of x, some kind of multiple of x out front to make this work. We don't have that here, so we can't use substitution. So instead, we're going to use the sort of method of last resort, which is integration by parts. So let's set f of x equal to the natural log of x squared and g prime of x equal to 1. Right, now it's kind of weird. We're setting, g prime equal to 1, and we're actually going to have g become more complicated instead of less complicated. So it's not really our normal practice, right? Normally we say we want to have f be something that becomes less complicated when differentiated, and g becomes something that stays the same. Here, g's can get more complicated. When you integrate 1, you get x. Integrate x, you get x squared, 1/2 x squared, and so on. So it's not quite a normal routine. However, note that differentiating f is going to give us some simplification. Now, recall from previous, so we'll do this again. How do you differentiate x? Well, here we're going to use the chain rule that we just talked about. Let's do it up here. So what's the derivative of f? I shouldn't even call this f. I'll call this h over here. What's the derivative of f? Well, the derivative of f is going to be, I should have done that again. Okay, I'll use r and s. So it's going to be, so f here, sorry, f is going to be r of s of x, where r is the natural log of x, and s is x squared. This is just like the example we did before, except with an x squared instead of x cubed, and no minus 1 outside, which is relevant anyway. So, derivative of natural log, and I said before I meant the previous problem session. Sorry, that might have been a little longer ago for some of you than it was for me. I'm doing these problem sessions after all the lectures, so I'm doing them in a row. So that's why I said after. Sorry. So s prime is 2x. So now we have r prime of s of x times s prime of x equals f prime. This thing over here is going to equal 1 over x squared times 2x, or 2 over x. So now we have f prime equals 2 over x, which is good. And then g is the integral of 1, which is just x. Let's ignore the c for now and put them in later. So now we can use the integration by parts rule, which says that the integral of fg prime is going to equal fg minus the integral of f prime g dx. Well, what's that going to equal? Well, f was natural log of x squared, and g was x, so it's x natural log of x squared, minus the integral of 2 over x times x, and here's the trick, and here's why we did this. The x's cancel. So this thing is x natural log of x squared minus the integral of 2 dx, or just x natural log of x squared minus minus 2x plus c, and we're done. So we did, again, a very complicated integral, using by parts, making use of the fact that when you differentiate a log, you get 1 over x. So in certain circumstances, you can cancel that 1 over x with existing x's and make it actually simpler overall, even if it violates the sort of general rule that we talked about in the lecture of trying to make f simpler and g stay the same. Okay, so there's that example from the book. Now I'll do a couple more that aren't in the book. Just to finish this off, here's one definite integral to give you an example of this. I should not erase the 2 screens ago. No, I did a different one here. Okay, so here is the definite integral. You do the inside stuff the same. So again, you're going to break it up using the fact that the integral is a linear operator, and break it up into pieces, and use the power rule in each particular case. So we're going to get 2 over 6 times x to the 6th minus 3 over 3 times x to the 3rd plus 6x. Now instead of adding a c here, though, as we would for an indefinite integral, we have a definite integral. This is evaluated from 2 to 3. That line means evaluated at 3, and then subtract the evaluation at 2. Well, evaluated at 3 is 1/3 3 to the 6th minus, that's just plain 3 to the 3rd plus 6 times 3. Then we'll do it again, evaluated at 2. So it's 1/3 2 to the 3rd, sorry, 2 to the 6th minus 2 to the 3rd plus 6 times 2. And after you go through and do the whole thing out, which I did elsewhere, assuming I did my math correctly, you end up with 208 2/3, but really that's not very important. The important part is this part right here. Okay, now almost done. We're going to do one substitution example. Just give it away. That's going to be this, 6x cubed minus 6x divided by negative x to the 4th plus 2x squared minus 5. x. Now again, this is complicated, so we want to first try substitution, because substitution is the great simplifier. Here, we might do it. So to substitute, we need to actually have a u that, when differentiated, cancel it out with a thing in front of the u. How do we do that? Well, what if u is this more complicated thing on the bottom, down here? Then our du is going to equal negative 4x third plus 4x dx. So this is the term that's going to end up dividing the previous one. Does that help us? So if we convert dx to 1 over negative 4x third plus 4x. Now here, remember the change of variable formula. Remember, there's sort of two ways to do it. One is to remember the change of variable formula, in which here is du dx. That's the easiest way to do it. Or you can just kind of take du dx equals du dx and kind of multiply both sides by dx. Not really accurate, but it's a way to remember this. Remember, the change of variable formula is du equals du dx dx. So this is the important change of variable right there. Divide through by this to get this here. That means this equals 6x cubed minus 6x divided by negative 4x cubed plus 4x, and then times 1 over u du. Well, this thing over here, that I'm now going to write in bracket in red, is equal to negative 3/2. So you can pull that out and get the integral of 1 over u du. The integral of 1 over u is the natural log of the absolute value of u. That's the one exception to the power rule. When you have x to the negative 1, the integral is a natural log of the absolute value. So we get the natural log of u plus c, which ends up equaling, plugging back in for u, the natural log of negative x to the 4th, absolute value of negative x to the 4th, plus 2x squared minus 5, and plus c. And that's it. There you go. That finishes up this problem session. Thank you very much.